Hello everyone, welcome to my class. In today's class, I'm going to cover tangent planes and linear approximations. Let me start the class right away. Our goal in this section is we wish to approximate the surface whose equation is z equals to f of xy around some point P by a plane called the tangent plane approximations or linearizations, that is linear approximations. So let me describe this diagram first. In the diagram, the surface is given in this brown color here, which equation is z equals to f of xy, and we are focusing on the point P. P is the intersection of two curves C1 and C2. If you remember, in our earlier sections, when we defined a partial derivative of f with respect to x and partial derivative of f with respect to y, we do have these two curves. Then these two curves have a tangent vector. Let's say T1 is a tangent on C1 and T2 is a tangent to C2. Then we have a plane containing that T1 and T2. That plane is this plane. This is the blue color plane here, and this plane is called the tangent plane. So let me define the tangent plane. That's better. Our tangent plane to the surface at any point P is the plane containing both the tangents T1 and T2, and its equation turns out to be as follows. Equation of tangent plane. So the equation of tangent plane, z equals to z0 plus fx, x minus x0 plus fy, y minus y0, and evaluate at point x0, y0. The tangent plane approximates the surface around the point of tangency and can be written as Lxy equals to the right side equation of the tangent plane equations, z0 plus fx, x minus x0 plus fy, y minus y0. Then this Lxy is called the linearizations, that is a linear approximation of fxy at point x0, y0. Quick note, if the partial derivatives fx and fy at point x0, y0 exist and are continuous, then we call f is differentiable at that point x0, y0. Next definitions: the total differentials or exact differentials dz or df. In calculus 1, for function of single variables y equals to fx, the del y equals to fx plus delta x minus fx. In the diagram here, this is the curve at any point here. This is the x, which is here the fx, and let's take a small increment delta x along the x. So the next point is x plus delta x. Then the corresponding change in y is delta y. So the f at x plus delta x, which is this value here, equals to this value, the whole value minus this value here. So the whole value is f of x plus delta x minus this value is same as this value, which is f of x. So delta y equals to f of x plus delta x minus fx. So we have the differential dy equals to f prime x dx. In calculus 3, for function of two variables z equals to fxy, and the corresponding change in z, if delta x is the change in x and delta y is the change in y, then del z turns out to be f of x plus delta x comma y plus delta y minus fxy. Then we have the total differential dz or df equals to, just similar to this one here, but here I do have the two first partial derivatives, so fx dx plus fy dy. So this forms and this forms looks similar. Note, since del z approximate dz, but dz is way easier to compute. So dz is this expressions and del z is this expressions. Awesome. In terms of linearizations of functions f at any point ab, we can write f approximated by lxy, where lxy equals to f of ab plus this total differential dz. Then this approximation is called the differential approximation, which turned out to be exactly the same as the tangent plane approximations. The tangent plane approximation is here. Awesome. Now let's move on. Quick remark. We can analogously extend these ideas to higher dimensions. Say for a function of 3 variables, the tangent plane approximation is f approximated by L, where L equals to w0 plus fx x minus x0 plus fy y minus y0 plus fz z minus z0 evaluated at x0 y0 z0. Similarly, the total or exact differential df or dw equals to fx dx plus fy dy plus fz dz. I hope this formula makes sense to you all. Now, with those formula, now let's compute some example. Example 1. Consider the surface or the functions given by z equals to f of xy equals to x squared plus 2y cubed and a point P with coordinate minus 1, 1, 3. Answer the questions A through F. So the part A questions, find the equation of tangent plane to the surface. So let's find the equation of tangent plane. First find the first partial derivatives of f with respect to x and y and evaluate those partial derivatives at a given point P and use the formula. So here fx is 2x, so this 2y cubed is a constant for x partial derivatives. Evaluate the fx at minus 1, 1, which turns out to be minus 2. Similarly, the partial derivative f with respect to y is 6y squared, evaluate at point P, which turns out to be 6. Hence by formula of tangent plane, z equals to z0 plus fx at P x minus x0 plus fy at P y minus y0. Great. So here z0 is 3, fx is minus 2, fy is 6, and x0 is minus 1, y0 is 1. So P, x0, y0, z0. So let's put those values on this expression. So the last line here, z equals to 3 minus 2 x plus 1 plus 6 times y minus 1. Simplify, it gives you z equals to minus 2x plus 6y minus 5. I hope this makes sense to you all. It's now part B. Find the linearizations of f at point P, or linear approximations of f at point P. This is simply Lxy equals to the right hand side of these equations of tangent plane. So then Lxy equals to minus 2x plus 6y minus 5. Great. Part C. Use the linearizations obtained in part B to approximate the functions fxy at the point Q, whose coordinates are negative 0.9, 1.1. So this point is close to the point of tangency. If our point is far away than point of tangency, then our approximation is worst approximations. So now let's use formula. Let's begin the solutions. So by formula, f at point Q is approximated by L at point Q. So that means to simply put x equals to on our part B on our linearizations result, put x equals to minus 0.9 and y equals to 1.1 and solve. So then minus 2, x is minus 0.9 plus 6 y is 1.1 minus 5, then foilate, add and subtract. This gives us 3.4. So we found the approximate value of functions at point Q is 3.4. Let's find the actual value of the functions at Q. The actual value is given by the equation of f, which is x squared plus 2y cubed. So here's f at point Q equals to the x squared, means minus 0.9 squared, plus 2 times y cubed, which is 1.1 cubed. So simplify, it gives us 3.47. So we are 0.07 off here. 3.4, 3.47. This is the approximate value of f at Q. This is the exact value of f at point Q. I hope this makes sense to you all. Quick aside, at the point R, minus 2, 2, this minus 2, 2 is further away than the point of tangency. Our point of tangency is negative 1, positive 1, but we are at negative 2 and 2. Then the exact values here, f at negative 2, 2 means at point R is turns out to be 20. So the exact value is 20. Our linear approximation is 3.4. So this our values will be worst approximations. Great. Now let's move on. Part D. So that the function is differentiable at point P. So what I need to show the differentiability, I need to show the partial derivative of f with respect to x and y exist and are continuous. So begin the solutions by part A. We found the partial derivative of f with respect to x at point P is negative 2, and partial derivative of f with respect to y at P is 6. So both of these values exist, and that means the partial derivative exists at point P, and at the same time these are the constants, so the constant functions are continuous everywhere. So both fx and fy exist and are continuous everywhere, means continuous at P, so the function is differentiable. I hope this idea makes sense to you all. Now let's move on. Part E. Find the total differential of the functions f of x, y. So use the formula. So by formula, total differential dz or df equals to fx dx plus fy dy. So fx is 2x, fy is 6y squared. So then total differential or exact differential df equals to 2x dx plus 6y squared dy. Part F. Compare the values of del z and dz when x changes from negative 1 to negative 0.9 and y changes from 1 to 1.1. That is from point P to point Q. Awesome. Now let's move on. So here dx is simply the change in x, so minus 0.9 to minus 1. So I need to subtract minus 1 from minus 0.9, which turns out to be 0.1, which is a delta x, and dy is change in y, which is 1.1 minus 1, turns out to be 0.1, which is delta y. Also derivatives of f partially with respect to x, fx is 2x evaluated at point P, which is negative 2, and partial derivative of f with respect to y, which turns out to be 6y squared evaluated at point P, which is 6. Thus, by formula, dz means the total differentials, dz equals to negative 2 is fx dx plus fy dy, so negative 2 times dx is 0.1, then plus fy is 6 times dy is 0.1. Simplify gives us 0.4. So dz, the total differential, turns out to be 0.4. Now on the other hand, the increment of g is del z. So del z equals to f of x plus delta x comma y plus delta y minus fxy, which is f at q minus f at p, f at q minus f at p. So f at minus 0.9 comma 1.1 was 3.47 we found earlier, and then minus f at minus 1, it turns out to be 3. You subtract 3.47 minus 3 equals to 0.47. Awesome. Now let's move on. Now quick aside, find the differential approximations of f at point q. Then by given formula, fxy approximated by lxy equals to f at p plus the total differential. F at p means f at minus 1 is 3 plus dz. dz is 0.4. So the 3 plus 0.4 turns out to be 3.4, which is the differential approximation. This is exactly same as the tangent plane approximations we found in part C. Let me show you. In part C, linear approximation or tangent plane approximation, which was 3.4. Awesome. So now let's move on. Now example 2. Find the equation of a tangent plane to the surface given by z equals to fxy equals to 2x square ey plus natural log x square over y plus 1 at point P with coordinate 1, 0. So now solutions. So now to find the equation of tangent plane, first find the partial derivatives of f with respect to x and with respect to y, and evaluate at point P and apply the formula. So here fxy can be written as here 2x square ey as it is. So here log of the quotient equals to difference of the log, so ln x square minus ln y plus 1. Take the partial derivative of f with respect to x, take y constant, so from here 3 to 4x ey plus 1 over x square times 2x is simply 2 over x, and this term is constant for x partial derivatives. Evaluate the fx at point P, turns out to be 6. Similarly, find the partial derivative of f with respect to y. Take x terms constant, so here fy equals to 2x square ey, this is 0, minus 1 over y plus 1. Find the value of fy at point P, which turns out to be 1. Also, z0 is put x equals to 0, so put x equals to 1, y equals 0 on this given equation of z, then that gives us z0. So here 2, 1 is square, e to the 0 is simply 2, and here ln 1 is square over 0 plus 1 means ln 1 is 0. So simply z0 is 2. I hope this makes sense to you all. Then by the formula, equation of tangent plane equals to z equals to z0 plus fx x minus 1 plus fy y minus 0. So here z0 is 2, fx is 6, fy is 1. Substitute here, simplify, it gives us z equals to 6x plus y minus 4. That's the equation of tangent plane. Awesome. I hope this makes sense to you all. Now let's move on. Example 3, the last example. Use differential to estimate the amount of tin in a closed tin can with radius 4 cm, height 12 cm, and thickness 0.04 centimeter. So let's find the dV here. So solutions here, dr is 0.04 and dh equals to on the top 0.04 and on the bottom 0.04, so total is 0.08 centimeter thickness. So that's why the change in height is 0.08. Awesome. Then the volume of the cylindrical tin can is given by V equals to pi r square h. So here pi is constant. So then dV equals to the total differential VR dr plus VH dH. So VR, so from here 2 pi r h times dr plus VH is pi r square times dh. I hope this makes sense to you all. Now let's plug the values. I think we have all the values available. So the left side is dV equals to 2 pi as it is, r is 4, h is 12, dr is 0.04 plus pi as it is, r square is 4 square and dh is 0.08. Now simplify. This turns out to be 5.12 pi, approximately 16.08 cubic centimeter. Great. I hope this makes sense to you all. Now we finished these sections, tangent plane and linear approximations. So thank you.